All right, so we're looking today at magnetic force on a current carrying wire, right? The last lecture was about magnetic force on a single moving charged particle, what force that feels. This is kind of an extension of that. So what's going to be the force on a current carrying wire that has a whole bunch of moving charged particles in them? And the objective for this one is D.2.A, and I'll read that to you. It's students should understand the force exerted on a current carrying wire in a magnetic field so that you can calculate the magnitude and direction of the force on a straight segment of current carrying wire in a uniform magnetic field. Right. So what's the force on a wire? Right. We know that. Well, if we remember from the last lecture, what was the magnetic force on a single moving charge? Right. FB. Anybody hopefully remembers that? Or have it in front of you. Right.
It was Q times V times B.
Q times V, yeah, Q times V cross B, right? So Q is the charge of the charged particle, and then V cross B, where this is the cross product, right? Where the magnitude of this is VB times the sine of the angle between them, and the direction we get right from the right-hand rule. All right, so that's the magnetic force on a single moving charge. So if we want to know the force on a wire, we have to remember that a wire has a whole bunch of moving charges in it. All right, so we're going to consider a wire that has length L and a current I is flowing through it. And we want to know what the magnetic force on that wire is going to be. Any ideas on how we would approach this?
Wouldn't it be
go
an
ahead.
integral?
It might, if the wire is perfectly straight and the magnetic field is uniform, then we don't need to do an integral. But
So we just get the charge density then and the length of the wire.
it is going to have to do with the charge density. Yeah. Let's look at it from a little more simply first. If we know that the force on a single moving charge, so one of the electrons in the wire, for example, is just Q times V cross B, how would I kind of expand that to a wire that has many moving charges?
Be the sum of all the charges.
Yeah, so we would add up the force on each of the charges, right? And if all the and if all of the charges are the same, right? Let's assume all the charges are moving straight down the length of the wire. So all the charges are identical. They're moving in the same direction with the same speed. What's a quick and easy way to figure out what the force is going to be on all of those charges?
I was just thinking, it's not current.
Well, the current is the total charge per unit time passing it.
Wait, then so we just multiply them?
Yeah, we multiply, right? We multiply basically just by the number of charges, right? So if I'm gonna give you a new, let's call capital N, where N is just the number of charges in the wire. Right, N is the number of charges moving in the wire. And here we would identify V with the drift velocity, right? Because if when we have a current flowing through a wire, we know that the average velocity of the charges in that wire is that V drift, which we learned when we first learned about current. So I'll put that V is the average drift velocity, right? And we say it's the drift velocity because we know that these charges are all moving around really fast in all kinds of directions, bouncing off of each other still. But if there's a current flowing from the electric field, we know that there's going to be an average tendency for the charges to move, if they're positive, in the direction of the electric field. And that's the drift velocity that we got when we were talking about current initially. So all we're saying is that the force on the wire with a lot of moving charges in it is that number of moving charges times the force on any particular charge. All right. So now we're going to rewrite this capital N. And you'll see why it seems like we're making it more complicated at first, but it's going to simplify out in the end. The number of charges, I can write N, the number of charges, as the number of charges per unit volume times the volume, right? And the number of charges per unit volume we can call the charge density. But lowercase n is what we'll use for the number of charges per volume. And then so times the volume, I'm going to write the volume as the area, the cross-sectional area of the wire times the length of the wire. All right, so I've got, so this N is charges, number of charges per volume. The L we've already identified at the beginning, but A is the area or cross-sectional area of the wire. All right. So number of charges flowing through the wire is just the number per unit volume times the volume of the wire, which is area times length. Okay, so far. So when we went back, when we first learned about current, right, and that was back in Surway and Jewett's section 27.1, what we found that current, which is just charge over, the delta Q over delta T, or dQ dt, the equation we got for that, which was just the number of charges per unit volume times the value of each of those charges times the drift velocity times the cross-sectional area. And you can go back to that lecture if you want to see where that came from, or reread section 27.1. Right, this was what we got for current, right? Current is the number, this is the total charge per unit volume, N times Q, times the velocity, right? Length per time times the area. So that ends up being a charge, total charge per time. All right, so now we're going to put it all together. So we know that the magnetic force from up here is Q times V cross B times this capital N, which we said is lowercase n times A times L, right? Number of charges times area times length of the wire. So let me rearrange that a little bit. All the scalars, all the ones that aren't vectors, I'm going to put together, right? That's the Q, the N, the A, and the L. So Q times N times A times L times the V cross B. And now I'm going to make a little bit of a switch here, because I know the direction. So this L is the length of the wire. And I know that the drift velocity is going to be along the length of the wire, right? The current flows along the length of the wire. So I can trade the vector. I can put the direction onto the length of the wire instead of the velocity. All right, does that make sense? Because the drift velocity is along the length of the wire. So I can rewrite this without really changing anything as Q times N times A times V, the speed, times L cross B. So I'm just giving the direction to the length of the wire instead of the velocity. But it's the same thing, because the drift velocity of the wire of the charges is always down the length of the wire. So do you see what I'm going to do next? What can I replace this Q times lowercase n times A times V with?
Current.
That's the current, right? These four together is the current. So that means I get for my magnetic force, the current times L cross B. All right, and so this is our result here, and this is true really for any straight wire. In a uniform field. Okay, so the magnetic force, so the bigger the current, the bigger the magnetic force. And then the length of the wire crossed with the magnetic field there, right? And we would use the to find the magnitude, right? L times B times the sine of the angle between them. And the direction we would get from the right hand. Right, so this equation is really just this equation for a whole bunch of moving charges in a wire. Right, so force on one moving charge, force on many moving charges going in the same direction down a wire of length L. Questions about this so far? We got one more little piece for this lecture. We still haven't looked at where the magnetic field comes from, right? Where this B field comes from. And we're going to get to that next. The first thing is to figure out what it does, right? What force we get on a moving charge if it is in one of these magnetic fields.
So does that mean that a wire will be almost like a magnet then?
Well, yeah, a current, yeah, if you have well, a wire with current flowing through it is going to be affected by a magnet, yeah.
But it's also going to generate its own magnetic field.
That's absolutely right. Yep. Yeah, so just like, it's pretty similar. When we first talked about electric fields, right? I made a big deal of, yeah, electric fields exert a force on charges, but also charges are what make the electric field, right, in the first place. And it's the same thing with magnetic field. A magnetic field is going to exert a force on a moving charge, right? And that's the only thing a magnetic field exerts a force on is a moving charge. And what we'll see in the next few lectures is that it's also a moving charge that produces a magnetic field. So anytime you've got current flowing, you've got moving charges, there are going to be magnetic fields.
I heard this somewhere, but is it like the change between the magnetic field and the electric field is like the speed of light?
Yeah, well, the speed of light, yeah, we're gonna actually see. Well, I hope we get to it. The very end, we see that the speed of light has to do with that epsilon naught, in Coulomb's law, and the equivalent mu naught in magnetism that we'll learn about soon. And yeah, the speed of light comes directly from, because all light is just
Electromagnetic wave.
Yeah, and an electromagnetic wave is just electric fields and magnetic fields kind of turning back and forth into each other and flowing along because of it. So yeah, the speed of light is very, very closely related to this stuff.
I was reading that. I ran across that when I was reading about Maxwell. It was pretty cool.
Yeah, that's what
I like discovered that.
Yeah, and it is a very cool it is a very, very cool way to kind of tie this stuff together at the end. Right, it produces a wave, right? Because if you have a, you can make a changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. And that's kind of for the same reasons that a moving charge produces a magnetic field and a stationary charge produces an electric field. So you can kind of see that if a changing electric field produces a magnetic field and vice versa, then you kind of get this wave that goes back and forth. And that's just light and how it propagates.
Yeah.
Mathematics of it are a little bit more complicated than we can do in this class, but not too much, and it is interesting. Okay, so one more little piece to this lecture. This is for any straight wire in a uniform field. But what if, and we're not going to do this out in detail, but what if the wire is not straight, or the field is not uniform? Then we're going to need to basically break it down. We would break our wire down into small lengths that are approximately straight. And small enough that the B field is uniform nearby. And what's the mathematical process or when we break down something into smaller or infinitely small pieces and then add them all up? That's just integration. Yeah, an integral. So what we get is that the magnetic force in that case is an integral of the current times dl, where dl is a small, an infinitesimally small length of the wire crossed with B. Okay, so we don't need to go into too much detail. We'll hopefully do an example of this in one of the problems that we get to later on. But this is what it's going to look like. And I believe this is how the equation is on the AP test equation sheet. But more often than not, in this class and even on the AP test, we'll be using it in this form, right, where we just have a straight wire in a uniform field. But if the wire is not straight, we break it up into little pieces of wire that are almost straight, and then we add them all up. That's that. All right. Any last questions or comments on the lecture stuff for today?
It makes sense. I think the difficult part is going to be when we start like the change in like seeing how the change in electric field is going to give us the change the magnetic field.
Yeah, and that's in Maxwell's equations right at the very end. And really, as far as the AP E&M test in this class is concerned, Maxwell's equations really you just kind of have to know they exist. The calc that comes from them is in multiple dimensions, and that's usually kind of out of the scope of the AP test.
Also, like in a question that tell us how we solve it, but they wouldn't ask us.
Yeah, you'll never have to on the AP test. You'll never have to actually use Maxwell's equations and solve from them. But you would in college freshman physics. That's kind of the borderline.
I see.
All right, so I'm going to stop the recording there. I'll make sure that this is up on YouTube if you need to go back and see this again.